Hello everyone. This is Sudhanshu Sarkar, Assistant Professor, Department of Electrical Engineering, Narula Institute of Technology. Today I am going to discuss a topic of Power System 1. The subject code is EE502. So this is the lesson plan of Power System 1. So in lesson plan, we have module 1, 4, 6 and 5 to 8. So from this module, today I am going to talk about the module 5, that is Corona. So in Corona, in our syllabus, as per the syllabus, total topics are principle of corona formation, critical disruptive voltage, visual critical corona discharge potential, corona loss, advantages and disadvantages of corona, and methods of reduction. So now I'm going to talk on three topics, that is the principle of corona formation, then critical disruptive voltage, and visual critical corona discharge potential. So these are the outcome of this Power System 1 subject. So in this subject, there are three outcomes: CO1, CO2, and CO3. So my today's topic of discussion is Corona. Today's topic of discussion, total subtopic I'm going to talk. That is, first one is the definition, second one is the principle of corona formation, third is the critical disruptive voltage, and visual critical corona discharge potential. So let's talk on the definition of corona first. The definition of corona is very simple. We have to remember only 3 points that are the important points for this definition. So corona is nothing but a phenomenon. So it's a phenomenon of violet glow, hissing noise, and production of ozone gas in an overhead transmission line is known as corona. So two figure is given here. Two figures actually are given here. So you can find that how corona produces in a real system. So please try to remember it's a phenomenon with violet glow, hissing noise. So these are the violet glow. You can find some violet glow. So you can observe very carefully that what is actually this violet glow. So with the notation, I can show you that the violet glow. So this part is actually the violet glow part. So you can find the glow here. Color is violet. Here also you can find the violet glow. This is all part. The whole section, the glow is there. Here violet. This is the violet glow. So through this part, you can find some glow. And hissing noise. When corona produce some noise produced, that noise is like hiss. So for that reason, it is called the hissing noise. And production of ozone gas. So for this effect of this violet glow and hissing noise, some ozone gas produces from the transmission line. So where it produces from the in an overhead transmission line. So this phenomenon you can find in the overhead transmission line. So that you have to mention this point very carefully. In an overhead transmission line is known. So all these three, the combination of these three phenomenon is actually called the corona. So this is actually the definition of corona. Now let's talk about the second topic, that is important one, principle of corona formation. So in principle of corona formation, we have to go through 2 points. So here we have to cover total 8 points, that how this corona formed from the overhead line. Look, for that, the first point, let's talk about the first point. Some ionization is always present in air. That means we know that in the air always some ionization is present due to the cosmic rays. So what is the reason for this ionization in the air? One, it is the cosmic ray. Fine. So the first one is the cosmic ray. Look, so the point is very important. We have to remember that ionization is always present. Ionization always present in the air. Where it is in air? Why? So where this will happen and why this will happen? So ionization is always present in air. Where? Air. Due to. So what are the reason for this? Why this? Due to cosmic rays, ultraviolet radiations, and radioactivity. So all these reasons, cosmic ray, ultraviolet radiations, and radioactivity are for all these reasons, the air is always ionized. Now, this is the first point. So you have to remember like this, that some ionization is always present in the air due to some cosmic rays, ultraviolet radiations, and radioactivity. Now move to the second point. Under normal condition, the air around the conductors contains some ionized particle. Okay, so what is this? Look, in normal condition, the air around the conductor. So if we move to the last slide, then you can find that, so air is there beside the conductor. These are the conductor, that overhead transmission line conductor. So here, under normal condition, there should be no abnormal condition. If the situation is fine, there is no storm, there is no ice, and if everything is okay, that condition is called the normal condition. The air around the conductors contain some ionized particle. So what are that ionized particle? So that ionized particle is basically some ionized particles. So what are that? That is basically free electron, that is free electron and positive ions. You can find some free electron and positive ion that is surrounded beside the conductor, and that particle is called the ionized particle. And neutral molecule. So without this, we find the ionized particle in the form of free electrons and positive ions and the neutral molecules. These, so two special particle. One is ionized particle, second one is neutral molecules. You can find beside the or around the conductor. This is second point. The first point is, please remember first point, ionization is always present due to the cosmic rays, Y, and ultraviolet radiation and radioactivity. Second point is, in normal condition, the air around the conductor contains some ionized particle, that is free electron, positive ions, and the neutral molecules. Now move to the third point. What is the third point? This is important. When PD means the potential difference. When potential difference is applied, so what we have to apply? Potential difference needs to be applied between the conductors. Potential gradient is set up. What set up? Potential gradient. I discussed what is potential gradient in the chapter of underground cable. So please watch that video, and then you will be very much you can gather the knowledge about the potential gradient. So what is this? When potential difference is applied, when the conductors, between the conductors, potential gradient is set up. So what set up? Potential gradient set up. Potential gradient is set up in the air, which will have maximum value. So what will happen? Which will have maximum value at the conductor surfaces. Which will have maximum value at the conductor surfaces. So for applying for the potential difference between the conductor, potential gradient is set up in the air, which will have maximum value at the conductor surfaces. So maximum value will appear at the conductor surfaces. Now move to number 4. What is number 4? under the influence of potential. So under the influence of this potential gradient, the existing free electrons are acquire greater velocities. So under the influence of potential gradient, the existing free electron acquire greater velocities. So this is our 4 point. 1, 2, 3, 4. We have completed this 4 point. Next, go to the next slide. The greater the applied voltage, the greater the potential gradient, and more is the velocity of free electrons. So what is this? Look, this is try to understand. The greater the applied voltage, that means if the applied voltage is very high, then what will happen? The greater the potential gradient. So potential gradient, the value of G will be increased. So it is directly proportional with applied voltage, and more is the velocity of free electrons. So if we increase the applied voltage, the potential gradient will be increased, and for that, what will happen? More is the velocity of free electrons. So free electron velocity will be increased. Now in point 6, when the potential gradient at the conductor surface reaches up to 30 kV. So this is the most important point. What is this? When the potential gradient, what is the potential gradient? If the potential gradient, that is the G, at the conductor surface reaches about 30 kV. If the potential gradient, that means G, if we increase the voltage and increasing, the potential gradient will increase, and in certain time, if the value of the potential gradient at conductor surface reaches about 30 kV per centimeter, that is the maximum value, the velocity acquired by the free electrons is sufficient to strike a neutral molecule with enough force to dislodge one or more electrons from it. Okay, so this is the reason 30 kV is a very important point. So please try to remember the potential gradient value, that is 30 kV per centimeter. That should be the maximum value. Then what will happen? For that reason, the velocity acquired by the free electrons is sufficient to strike the neutral molecule with enough force. So to dislodge one or more electrons from it. So these are the point. Number 6 is the most important point you have to remember. That means the voltage should be 30 kilovolt, the potential gradient per centimeter. Then the velocity acquired by the free electrons is sufficient to strike the neutral molecule. So there should be some neutral molecule and sufficient to strike. That velocity will strike free electrons, sufficient that free electrons will strike the neutral molecule and with enough force, and that dislodge one or more electrons from it. Okay, so the next point, number 6. Number point is the next important point. This produces another ion. So for the effect of point 6, another ion and one or more free electrons. So for that reason, another ion and one and more free electron will produce, which in turn are accelerated until they collide with other neutral molecules, thus producing other ions. So in this way, other ion will produce. How? This produces another ion and one or more free electrons, which is turned or accelerated until they collide with other neutral molecule that produces another ions. So in this way, another ion will produce. This process of ionization is cumulative. Okay, so in this way the process will continue. So this process is basically a cumulative process. So these are the figure and different overhead transmission line figure where the corona is producing. If you follow, you can find very easily that here the corona is producing. In this point, corona is producing violet glow, hissing noise, production of ozone gas. In this part also the ozone is producing, here also. So through the line, look very carefully, through the line the ozone is changed, violet glow is there. Here also the ozone violet glow you can find from this position. So in this way the corona produced through the overhead line. So this point, in this point also you can find violet glow. Okay, so three phenomenon: violet glow, hissing noise, and production of ozone gas is known as corona. Now move to the next slide for the next part of the. So the previous point is actually was that how the corona, principle of corona formation, how the corona formed from the overhead transmission line. This is the figure. It's a very good and very important figure. If you go somewhere at night and if you are sometime, if you are moving or nearest to the overhead transmission line, if you are below the transmission line, sometime you can find it, the corona effect. Will find some noise, you can find some glow like this. So that is actually the effect of corona. Now move to the next slide, that is critical disruptive voltage. Now the mathematical formation is going, we are going to discuss on that topic. So what is that? So what is critical disruptive voltage? It is the minimum phase neutral voltage at which corona occurs. So we have to remember only this part. Which part? Minimum phase neutral voltage. Minimum phase neutral voltage. Some voltage between phase and neutral at which corona occurs. So that is critical disruptive voltage. Now, for that, for the proof of this critical disruptive voltage, we have to consider two conductor at least. Two conductor. So what is the point? The point is we need to consider two conductors. So consider two conductor of radius. What will be the radius? The radius of r centimeter and the spaced d centimeter apart. That means the space between two conductor is d centimeter. So now the question is, what is space? Fine. So let me show you what is space. Look, this is the space actually. This is actually the space between two conductors. Look here. This is the space between two conductors. This is the space between two conductors. This is the space between two conductors. Okay, I think now it's easy for you to understand. This is the space between. This is the another space between the conductors. So this is called the space between the conductor. So the point is very easy to remember that what is actually the critical disruptive voltage. I already discussed this, that it's the minimum phase neutral voltage at which corona occurs. Minimum phase neutral voltage. So that much of voltage needs to be reached. So for that we have to consider two conductor of radius smaller centimeter and spaced small d centimeter apart. So I already showed what is the distance. So that is the distance spaced. So that should be the space. If capital V is the phase neutral potential or phase neutral voltage, then potential gradient at the conductor surface is given by, so this equation we already proved in underground cable. So you can go there and you can learn that what is this potential gradient. I already discussed on this topic several times about the potential gradient. is the conductor surface. So then the potential gradient of the conductor surface will be given G equals to V divided by smaller log d by r to the base E volts per centimeter. So the unit of the potential gradient is volts per centimeter. So the total equation of the potential gradient is G equals to V. V is the phase neutral potential divided by R. R is the radius of the conductor. Log d by r is the space between the conductor and R is the radius of the conductor. So G equals to V divided by small r log small d by small r to the base E. So this is the equation of the potential gradient. Now, in order the corona is formed, the voltage, the value of G must, for the formation of corona, the value of G must equal to the breakdown strength of air. Next important point. So what is the point? The point is the value of G must be made. The value of G must be made equal to the breakdown strength of air. The breakdown strength of air at 76 centimeter pressure and temperature 25 degree centigrade is 30 kV. I already said 30 kV per centimeter maximum value, that is the value, or 21.2 kV per centimeter RMS value. RMS means we have to divide 30 kV by root 2. 30 by root 2. So that is the maximum value. Dividing with root 2, we'll find the RMS value, that is 21.2 kV. So, and so what is actually this? Look, let me talk very simple mathematics on this 30 kV. So 30 kV divided by root 2. If we divide 30 by root 2, we'll find 21.2. So 21.2 kV per centimeter RMS, and is denoted by, and we can denote it with G suffix 0. If Vc is the phase neutral potential required under this condition, then G0 equals to Vc divided by R0 log d by r to the base E. Same thing, but here G convert to G0, V convert to Vc, R convert to R0. So same equation, the previous equation is same. So in this way, we can find the phase neutral potential required under this condition. We can recall the equation, same equation, but here we are just converting it from G to G0. Again repeating for the understanding or remembering of you the equation. G0 equals to Vc by R0 log d by r to the base E. Critical disruptive voltage Vc equals to G0 R. So from here, this is the equation of G. So from here we can find easily the value of Vc, that is the critical disruptive voltage, Vc. V for voltage, C for critical. So critical disruptive voltage, so simple multiplying, we can find Vc equals to G0 R log d by r to the base E. However, if these conditions vary, so if this condition vary, the air density also changes. So the density of the air will also change, thus altering the value of G0. Okay, so the value of G0 will alter, obviously. The value of G0 is directly proportional to air density, and we know that the value of G0, the potential gradient, is directly proportional to the air density. Thus, the breakdown strength of air at a barometric pressure of B centimeter of mercury and temperature of T degree centigrade becomes delta G0. So after changing, so something is changing here. So what is changing? Look, if this condition vary, I am considering that the condition, standard condition is Vc equals to G0 or log d by r to the base z. Now, if the condition vary, this condition vary, then what will happen? The air density also changes, that altering the value of G0, the value of G0 is directly proportional, but we know that this is directly proportional to the air density. Thus, so what will happen? Thus, the breakdown strength. What is the breakdown strength? Look, the breakdown strength of air at barometric pressure be B. We are considering the barometric pressure. The breakdown strength of air is B centimeter and of mercury, and temperature is T degree centigrade, becomes this one, delta G0. First it was G0. Now after changing all the parameters, it is becoming delta G0, where delta is the air density factor, and we can explain this delta with 3.92 B divided by 273 plus T, where B is the barometric pressure of B, that is the breakdown strength of air B. So 392 B divided by 273 plus T. T, what is T? Centimeter mercury, and temperature T degree centigrade becomes delta B. So the value of delta is the density factor. So delta is the density factor, and the value of this delta is 392. Remember this for MCQ or some interview questions. The value of this, the small changes after changing all the parameters, the delta is the density factor, and that is equals to 392 B. B is the breakdown strength of air divided by 273 plus T. V. So this is the value of delta. Now to the next slide. Under standard condition, the value of delta equals to 1. Standard condition, that is already we discussed. So if it is 1, then no problem with this equation. So if it is 1, then Vc, the critical disruptive voltage Vc, again I am noting that Vc is equals to G0 delta R log d by r to the base z. So if delta equals to 1, so no problem with the system, the condition, standard condition, if delta equals to 1. Please remember, this is also important questions or important term. It will help you in different places in your engineering study and engineering profession. It will help you a lot. So because this corona effect is directly related with the field work, if you move to the industry where the erection part, transmission line erection part is there, so you have to deal with all of these equations for the setup, for the erection, for the stringing of the overhead transmission line, where tower will be there, conductor will be there. So correction must be made for the surface condition of the conductor. Surface condition of the conductor. This is accumulated for by multiplying the above expression by irregularity factor M0. So how can we correct this situation? So you can, correction must be done for the surface condition of the conductor, where the surface condition of the conductor, thus accounted for by multiplying the above expression by irregularity factor. So what is the irregularity factor? That is M0. Now we'll discuss about what is M0. Look, the modified equation, critical disruptive voltage. Vc equals to, we know that from the previous equation, we know that Vc equals to G0 delta R log d by r to the base z. So here we are modifying and we are multiplying M0 with the equation. So the new equation will be equals to Vc equals to M0. Only this part we add here. G0 delta R log d by r to the base z kilovolt per phase, where M0 equals to 1 for polished conductor. So here the new part we add M0. So the value of M0 will be equals to 1 for polished conductor. The value of M0 will be 0.98998 to 0.92 for dirty conductor. The value will be 0.87 to 0.80 for standard conductor. So you have to remember all this. These values are very important for the corona study, for the finding the critical disruptive voltage, that the value of M0 will be equals to 1 for polished conductor. For dirty conductor, the value of M0 is 0.92 to 0.98. And for standard conductor, the value of M0 should be equals to 0.80 to 0.87. So you have to remember all these. Now, go to the next slide. What is the next slide? In the next slide, you can find visual critical corona discharge potential. Now the question is, what is this visual critical corona discharge potential? So visual critical voltage potential, discharge potential means the voltage. So it is the minimum phase neutral voltage at which corona glow appears all along the line conductor. Now I think all of you are very much clear about the concept of visual critical voltage. It is the minimum phase neutral voltage at which corona glow appears all along the line conductor. Where? All along the line conductor. If the glow appears, then it is the minimum voltage. For the minimum voltage, phase neutral voltage should be that one which corona glow appear all along the line conductor. Fine. Now, let's talk about this visual critical voltage. It has been seen that in case of parallel conductors, the corona glow does not begin at the disruptive voltage Vc, but a higher voltage Vv, called visual critical voltage. The phase neutral effective value of visual critical voltage is given by the following empirical formula. So what is the formula? Let's talk about the formula. So here the formula is Vv equals to visual Vv mv. So the last was m0. So for this case, this is mv. That was vc, and here it is vv. Now m0 converted to mg. G0 delta R is same. So inside this new term is coming, that is 1 plus 0.3 by root over delta R log d by r kV per phase. So this new term, new part is coming in this equation additionally, that is 1 plus 0.3 by root over delta R, where mb is another irregularity factor having a value 1 for polished conductor, 0.72 to 0.82 for rough conductor. Just remember this, mv 1 for polished conductor, and it is 0.72 to 0.82 for rough conductor. So the next slide, let me discuss or talk about a very simple problem, what we understand. So what is the difference between these two, please? Critical disruptive voltage, that was Vc, M0 G0 delta log d by r, and visual critical voltage Vv, Mv G0 delta. So new additional part 1 plus 0.3 by delta R log d by r. This new term is coming for the visual critical voltage. And I discussed the other part. Now it's a very simple example. Let's consider a three-phase line has conducted 2 centimeter. Three-phase line has conducted 2 centimeter of diameter spaced equally 1 meter apart. If the dielectric strength of air is 30. Dielectric strength of air is 30 kV maximum per centimeter. So we have to find disruptive critical voltage for the line. Okay, take air density D equals to 0.945 and the irregularity factor M0 equals to 0.89. So first, to solve any type of problem from power system or the other subject related topics, first please write all the given values. So what are the values given here? So here the diameter is given of the conductor, so we have to find the radius of that conductor. So diameter is here 2 centimeters. So what will be the radius? Diameter by 2. So that means the value of R equals to 2 divided by 2. So it will be 1 centimeter. Now conductor spacing D equals to 1 meter. That is, we have to convert it to 100 centimeter because R is in centimeter and the space we need to convert it to from meter to centimeter. The dielectric strength of the air G0 equals to 30 kV per centimeter. That is also given, or in RMS form after dividing by root 2 the value of 30 kV will be converted to 21. So it is 21.2 kV RMS per centimeter. Okay, so that part is also measured. Now the next slide, we have to find the disruptive critical voltage, that is VC. So what is VC? M0 G0 delta R log D by R kV per phase RMS value. So now put all the value which you already find or from get it from the given values, that is M0 0.89, G0 equals to 21.2, delta 0.945, R is 1, log 100, D equals to 100 centimeter divided by 1. So after calculating, we'll find the value of the critical voltage, disruptive critical voltage equals to 82.1138 kilovolt per phase. So the line voltage RMS value will be root 3 into 82.1138 kilovolts. So in this way, we can find or we can solve the problem related with the critical disruptive critical voltage. And also if the problem is related with visual critical voltage, so for that case, we need to use this formula. So in this way, we can solve any problem of disruptive critical voltage and visual critical voltage. So that's all about today's lecture. So as a reference, I use the book Principle of Power System by V.K. Mehta and Rohit Mehta. And finally, thank you everyone